Control System 1, today we will discuss on root locus techniques. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In this video, we will discuss on the introduction of root locus techniques, the locus of roots of characteristic equation, Evans condition, the rules for the root locus techniques, and the examples. Now, the relative stability and the transient response of a closed loop control system are directly related to the location of the closed loop roots of the characteristic equation in the S-plane. For finding the stability of a system, the Routh-Hurwitz criteria can be applied to the characteristic equation, but it has some drawbacks. So let's check what are the drawbacks of Routh-Hurwitz criteria. First, it does not give sufficient information about the relative stability of the system. Relative stability means the amount of overshoot, settling time, etc. Now, sometimes due to this poor stability, the system may be in the verge of the instability. And secondly, it does not help much in design problems when it is required to achieve the desired performance by varying one or more system parameters. Now, the root locus technique is a graphical representation as domain is introduced by W.R. Evans in 1948, and it is extensively used in design of the control system. And this graphical method for sketching the locus of the roots in the S-plane as a design parameter of the system is varied. That means the locus of roots of the characteristic equation when gain is varied from 0 to infinite is called the root locus. And with this help of root locus, we can easily predict the performance of the whole system. And the root locus is symmetric about the real axis or the x-axis. So here we are considering that the transfer function, that is the open loop transfer function, is given as k by s into s plus p. From this equation, we can say that open loop poles are located at 0 and at minus p, whereas the feedback is used here minus 1. So, the closed loop transfer function, that is denoted by cs, can be calculated as k by s square plus sp plus k. So, the characteristic equation becomes s square plus sp plus k. So, this characteristic equation gives the two roots of the system. As the order of the equation is 2, that means there are two roots present in this system. And these two roots are, according to the Sridhar-Acharya formula, minus p plus minus root over p square minus 4k by 2. So, for any positive values of p and k gives the roots in the left hand side of the S-plane. The relative stability of the system depends on the location of the roots. Now, k and p both can be varied, though k is generally used as an adjustable parameter, as adjusting k can be made by including the proportional gain in series with the system. Now, the k can be varied from 0 to infinite, then we can obtain the loci of the roots in the S-plane. And the relative stability depends upon the location of the roots. So, first we can consider that the k is varying from 0 to infinite and open loop pole locations are at 0 and at minus p. So, for the case 1, if we consider k lies between 0 and p square by 4, then for putting the value k is equal to p square by 4 in this equation, you can find out that s1 and s2 are real and equal, and the value of s1 and s2 is minus of p by 2. So, when k is 0, then then we can find out that here S1 and S2 are 0 and minus P. That means the K starts varying from 0. The S1 starts moving from 0 towards this direction, and the pole at minus P starts moves in this direction. That means the directions are opposite. And at K, that is equal to P square by 4, both the roots meet at minus P by 2, because at P square divided by, when K is equal to P square divided by 4, this S1 and S2 becomes minus P by 2. So both the roots start from this open loop position and start to move in this opposite direction, and at K is equal to P square by 4, they meet the point this minus P by 2 or minus 0.53. And if then we are varying K greater than P square by 4, then we are getting that the pole locations are minus P plus J into root over P square minus 4K by 2, and S2 becomes minus P minus J root over P square minus 4K by 2. That means the root locus moves vertically in the opposite direction and tends to infinite as K tends to infinite. That means when K is varying, for this pole it goes to the left hand direction, and for the minus P pole it goes to the right hand direction. At K is equal to P square by 4, they meet this point, and further increasing the value of K, then the P square by 4, it moves vertically in the opposite direction and goes to infinite. Next is the Evans condition. Now the general characteristic equation is given as 1 plus GSH is equal to 0. And we can say that GSH is equal to minus 1. So from this, as the A is the complex variable, so the magnitude criteria becomes, it gives the mode of GSHS is equal to plus 1, and the angle criteria becomes plus minus 180 degree into 2Q plus 1, where Q is varying from 0, 1, 2, etc. Now, for the angle condition, the angle condition is also known as the angle contribution. Now, for the magnitude condition, the values of A, S which fulfill both the angle and magnitude conditions are the roots of the characteristic equation at the closed loop pole. Now, G of S into H of S is equal to minus of 1, and this minus of 1 can be expressed as minus 1 plus J0 in the complex notation. Or this point minus 1 plus J0 is a point on the negative real axis, and it can be traced as magnitude 1 at the angle plus minus 180, as well as then the complete rotation, that means we are adding 60, so it gives the 540, then 900 and so on. So it can be generalized form like this, 180 degree into 2Q plus 1. And if a point in S plane has to be on the root locus, then it has to satisfy the angle condition. And the angle of GSHS calculated at the point must be an odd multiple of plus minus 180. And the angles are measured in the counterclockwise direction from the horizontal line, and horizontal line is used as a reference, and we are considering that horizontal line is 0 degree. And any point on root locus must satisfy either the magnitude condition or the angle condition. And since K is not known in the function GSHS, so we can't determine mod of GSHS at any plane. Hence, the magnitude condition is unsuitable to check the existence by any point on the root locus. So in this case, first we need to apply the angle condition to determine whether a point in the S plane lies on the root locus. And if this condition is satisfied, then we can use the magnitude condition to obtain the value of k, for which this will be a root of the characteristic equation. That means the magnitude condition and the angle condition are not independent on another, and one implies the other. And the root locus can be drawn by checking the angle criteria at various points of the S-plane. And a number of points in the S-plane are located where the angle criteria is satisfied. So next we will consider some root locus rules. And first we need to keep in mind that the root locus is symmetrical about the x-axis or the real axis, and we will construct the upper half of the root locus, and the bottom half of the root locus can be drawn once the locus above the real axis has been determined, and it will be the mirror image of the upper half. And so first we need to find out the number of locus, and the number of locus is same as the number of open loop poles of the transfer function. And the root locus branches start from the open loop poles and terminate at open loop zeros, and if there is no open loop zero, then it will terminate to the infinite. And the number of branches terminating to infinite is given as n minus m, where n is the number of poles and n is the number of zeros. That means the branches will start from number of poles n, and it will terminate at open loop zeros. If zero is not there, then it becomes the terminating to the infinite. And a point on real axis lies on the root locus if the sum of the poles and zeros on the real axis to the right of the test point is an odd number. And next is the asymptotes of the root locus. An asymptote originates from the centroid and it goes to infinite at a some definite angle. An asymptote provides the direction of the root locus when they depart breakaway points. An angle of asymptotes can be calculated as 2q plus 1 into 180 by n minus m, where n is the number of poles and n is the number of zeros. And q is varying from 0, 1, 2 up to n minus m minus 1. Next is the centroid, and from the centroid the asymptotes originates, and it is defined as the point of the plot where all asymptotes start, and mathematically it can be calculated as the sum of the real part of the poles minus sum of the real part of zeros divided by n minus m. N denotes the number of poles, whereas m denotes the number of zeros. And then we need to find out the breakaway points, and the breakaway points are those at which the multiple roots of the characteristic equation occurs. And the value of k is maximum at the points where the branches of root loci breaks away. And breakaway points may be real, may be imaginary, or the complex. And breaking point means the root locus must be present between the two adjacent zeros on the real axis. Next is the angle of arrival or departure. Now, angle of departure is calculated when there exists complex poles in the system. And angle of departure phi p becomes plus minus 180 into 2q plus 1 into phi, where the phi is the net angle contribution to the pole by all other open loop poles and zeros. So angle of departure becomes 180 minus of this angle contribution from different poles, that is phi p1, phi p2 plus phi p3 etc. minus sum of the angles to a complex pole from the zeros that are dependent on the phi z. So this is the phi p, and the sum angle to the complex pole from zeros becomes the phi z, and the angle of departure is phi. And for the intersection of root locus with the imaginary axis, we need to use the Routh-Hurwitz criteria to find out the point of intersection of root locus with the imaginary axis. And we also need to find out the auxiliary equation, and for then we can find out the corresponding value of k, which gives the value of the point of intersection. So let's take an example. Here, transfer function is given and we need to find out the breakaway point. So here, k into GSHS is given as k into s minus 3 into s minus 5 by s plus 1 into s plus 2. So from this, we can multiply this 2 and it becomes s square minus 8s plus 15 by s square plus 3s plus 2. Now, k into GSHS is equal to minus 1. Or putting the values of k into GSHS, we can find out the value of k. Now, the breakaway points, that means points at which the multiple roots of the characteristic equation occurs, can be find out by using the solution dkds is equal to 0. So dkds becomes 0, and we can find out the dkds by differentiating this k relation with respect to s. And then we can find out that value of s, which becomes minus 1.45 and 3.82. So the open loop pole locations are minus 2, and here the open loop pole location is minus 1. So two poles are denoted as minus 1 and minus 2. And this is the S plane, the real axis, or which is represented by sigma, and this is the imaginary axis and represented by j omega. So first we need to draw the open loop poles, that is at minus 1 location and minus 2 location, and then we can find out the minus 1.45 is the breakaway point. So at minus 1.45, both poles are moving towards this breakaway point, and at this point they can going in this direction. And similarly, we can find out that this point 3.82, from this it can be goes to the zeros. So 0 locations are 3 and 5. So for the first one it goes to 3 and then another branch goes to the 5, because as per the rule, the root locus branches will start from the open loop pole locations and it will terminate to the open loop 0 locations. So let us take another example. So here open loop transfer function is given and we need to find out the asymptote and the centroid. Now here we can say that open loop poles are 0, minus 1, minus 2 and minus 4, where open loop 0 is minus 3. So from the formula we can find out the sigma, that is equal to real part of the poles of open loop transfer function. So all the poles are the real poles. So the real poles are 0, summation of the real part of poles, that gives 0, minus 1, minus 2, minus 4, minus the real part of 0. So it is also a real 0, so it is located at minus 3 position. So we are taking here minus 3 divided by number of open loop poles minus number of open loop zeros. So here there are 4 poles, those are 0, minus 1, minus 2, minus 4. So number of poles is 4 and there is only one open loop 0, that is 1. So it gives us minus 4 by 3. And from this point, this is the centroid, and from this point the asymptote will generate. Now for the asymptote we need to find out the value of q, and q is varying from 0 and 2 up to n minus m or p minus z minus 1. So number of poles is 4 minus number of z is 1. So 4 minus 1 becomes 3 minus of 1, because the formula is n minus 1. So q will be calculated for 0, 1 and 2 only. So there will be 3 asymptotes. So if we put the value q is 0, 1, 2 varying here, then we can find out the values of asymptotes at 60 degree, 180 degree and 300 degree. So from the centroid we can draw the 60 degree line, 180 degree line and 300 degree line. So in this way we can find out the asymptote and the centroids. And here another thing we can say that in one rule we have said that a point on the real axis lies on the root locus if the sum of the poles and zeros on a real axis to the right of the point is an odd number. So here we can say that these are the pole locations and this minus 3 is 0 location and it is also the pole location. So if we consider any test point between 0 to minus 1, then at the right hand side of the test point the number of poles plus zeros will be 1, which is an odd number, and that indicates the between 0 to minus 1 all the points are located on the root locus. Whereas if we consider a point in between minus 1 to minus 2, any point in between this region, then we can say that to the right hand side of the test point the total number of poles and zeros is equal to 2, which is an even number. So any point in between minus 1 to minus 2 is not in the root locus. Again, for minus 2 to minus 3, if we consider, then for this test point all the points to the right hand side has total odd number of poles, that is 3. So all the points in between minus 2 to minus 3 is located in the root locus. Whereas the test points in between minus 3 to minus 4, the total number of poles and zeros is 1, 2, 3, 4. That is the even. So in between minus 3 to minus 4, it will never lie in the root locus. And using the same theory, we can say that minus 4 to infinite, the number of poles plus zeros becomes 5, which is an odd number. So minus 4 to infinite will always lie in the root locus. These are the references, and in this video we have discussed on the different rules of the root locus techniques, which will be very important to find out the root locus of a given system. So in the next video we will discuss on the problems on root locus, which will be based on the rules of which is shown in this video. So thank you. Hope after this video lecture you have a clear idea about today's topic. Now we will go through some questions and answer session in the context of this video lecture. Now you are requested to go through gradually and try to solve the MCQ questions by your own. Answers are also attached at the end of each question.